I'm here this morning I'm John Orchid. I'm the Deputy Director for Research at the Scripps Institution of Oceanography, and it's my pleasure to open the morning talk by introducing the speaker this morning, Walter Munk. Walter is one of the most prolific young scientists at the institution today. He's done a lot of work. He's called a physical oceanographer, but his interest and breadth is substantial. In the 50s, he wrote a landmark book on the rotation of the Earth, the solid Earth, and the problems associated with that. And it remains a classic today. And it was an unusual time in the computational history of science, in that it was able to be done that early and extend its reach so far. He's looked at the propagation with his kids and wife, propagation of waves from the deep Southern Ocean around Antarctica to the shores off La Jolla. He's worked on acoustic thermometry, measuring the temperature of the ocean basins with great accuracy. He's worked on tides in his career, and the thing that he'll be talking about today is sea level, and I'll say a little bit more about that shortly. Walter's got a huge number of awards, and I'm sure you'd just assume I didn't mention them. I know that Judy keeps them all in a drawer in the bedroom rather than on the wall, and it's full. But Walter's a member for some time of the National Academy of Sciences and Thomas Jefferson's American Philosophical Society. He's won the senior medals of many scientific organizations, including the Bowie Medal of the American Geophysical Union, the Day Medal of the Geological Society of America. In the 80s, he was presented with the National Medal of Science by President Ronald Reagan. And more recently, he won the Kyoto Prize and had the opportunity with Judith to meet the Emperor of Japan. So he's well known for his research in all these different areas. And it's kind of interesting that a study that he began in sea level some years ago in the early 70s actually has come back. In the early 70s, Walter advocated gates at the three entrances to the Venice Lagoon in order to limit the tides, the high tides, from encroaching on Venice itself, as Venice seems to be sinking. Oh, that's still an issue in its own right, as you'll probably see later today, although Walter's, I think, not talking about Venice today either. St. Mark's, though, finds itself underwater the majority of the year these days, and it's become a huge problem. The idea has actually been finally, after 30 years, picked up by the government and by Venice itself. The idea of erecting these gates is now a thing that is very likely to happen, but probably still on Venetian timescales. The problem they run into has to do with pollution. You can imagine Venice with this lagoon that doesn't flush well, that's been there for, 1,000 years. The sediments are badly contaminated in the area, and they've come to Scripps specifically with one of these things that only Venice could possibly do, a sole source grant or contract to study the contamination of the soils that need to be moved in order to erect the gates. Current law prevents these sediments being moved around anywhere, but of course you can't build the gates until you're able to do that, so they're asking Scripps for an opinion on the classification of the sediment contamination and its effect on biology in order to cross this hurdle. So it may well be another 30 years before Walter's gates are actually erected in Venice. But one of the ideas and one of the concerns that people have today is that limiting the flushing of the lagoon, is what their perception is, by the tides will further contaminate the thing. Walter's original solution would actually use the timing of the tides and the gates to flush the lagoon more aggressively than is being done now. So it's odd and interesting that after all these years, this study of Walter's returns to Scripps again as we next month go over to Venice to design this program for the city. But it's not clear whether Venice, I guess, is rising or sinking. It clearly is sinking. But one of the other projects that Scripps has been operating now for about 3 years is actually measuring the rate at which Venice is sinking by using the global positioning satellite system. And so there are several buildings in Venice actually have these antenna on top, and we're watching as it slowly sinks into the ocean. But the thing that Walter, I think, will talk about today is that the sea is also rising. The sea level today is increasing, and his talk today, not about Venice, I think, but is the global sea level and Enigma. So, Walter.
Well, thank you for this early morning introduction, John. And since you said I wasn't going to talk about Venice, I have to start saying something about Venice. Sea level today, at this time, is going up about 3 millimeters per year. It's about a foot per century. Not very much. But among those of you who own a Grand Palazzo at the Grand Canal in Venice, you will have by now, at that rate, have lost your bottom story. You see, a foot a year and 500-year-old house means that your bottom 5 feet of your house is now flooded. So, in that sense, it's a very real number. But the importance of sea level is not so much that it's affecting some people who live very near to the water, but that it's a good indicator of climate. The heat stored due to global warming is mostly in the ocean, and when the ocean is warmed, it expands and the sea level rises, so that sea level is a good indication of heat storage. And that's really the principal reason people are interested in sea level. But if you live by the beach in regions where there's a very flat slope, then of course a rise of 1 foot could mean that you lose 100 feet of frontage because of the very small slope, and then you would be concerned. Now, the subject is a complicated one, and I hope that I didn't plan to cover too much ground. I'll try and say it as succinctly as I can. Now, there are 3 problems. One is, how fast is sea level rising? And I mentioned the present rate is 3 millimeters per year. Perhaps you could remember that because we're going to compare it to similar numbers in the past. The second question is as to why sea level is rising, and I mentioned 1, thermal expansion, water getting warmer, sea level goes up. There is a second cause, also related to climate. If glaciers are melting and more water is added to the oceans, then sea level is rising as well. And so the other 2 questions are, how much of the observed rise is due to warming, how much is due to continental melting? Those are the 3 first-order questions that we would like to see answered when we talk about this subject. Now, what you see here in my first transparency is the glaciation for the last 20,000 years. You notice I marked this transparency as last 10,000 years. And actually the left top one is the situation 20,000 years ago at the maximum of the ice age. The Bering Seas on the left. So this is North America, this is the Atlantic, and you see large area covered by snow and ice. By the time we get to 12,000 years ago, and and 10,000 years ago here, the situation has more or less stabilized. There isn't terribly much more melting since that time. Now, the removal of the ice cap does 2 things. One is that the melting goes into the ocean and raises the sea level. The other is that when you remove the load of ice from the continents themselves rise. Just like if you put additional load, it'll be pressed downward and sinks. It'll rise, and a solid earth will flow is the right word, towards the regions from which the ice has been removed. And since the ice is being removed in regions of the far north, these projections are centered on the North Pole. There will be movement away from the equator towards the poles, and I think you can see that the moment of inertia of the Earth would diminish as you move towards the axis of rotation. Now the next slide shows a sort of a symbolic plot of global sea level against time on that 10,000 year time scale. And sea level, as a result of the glacier disappearing, has gone up, and the scale is not visible on the left, has gone up about 120 meters, 360 feet. And notice that nearly all of the sea level rise is completed about 4,000 years ago. The rise during the height of the deglaciation on the left here was at 10 millimeters per year, 3 times of what the rate is today. And after that, in the region to the right, it's probably less than 1 millimeter per year on the average. And so do remember that there are these two effects: the flow of Earth towards the regions that are deglaciated and the change in sea level itself. Now the interesting thing is that the ground on which we're sitting here in La Jolla and elsewhere in the world is still changing. In the north, moving up at a rate which is dependent on what happened 20,000 years ago. And one of the difficulties of measuring sea level is that the Earth itself is still recovering and for other reasons moving, and is doing that in response to what happened at the last glaciation. Now, what happened in the last 1,000 years? And this is a bit of a complicated transparency, but it's one of the most interesting things that men have ever done. It shows the rotation of the Earth in the last 3,000 years. It goes back to 500 years before Christ and ends today, and it infers the change in the rotation of the Earth as deduced from solar and lunar eclipses. Now the way this is done is as follows. If the Earth were spinning at a precise rate without changing, you could calculate backwards 3,000 years exactly when and where eclipses should occur. It turns out they don't occur as predicted, and the Earth as a timekeeper since Egyptian time has lost 15,000 seconds or 4 hours. And the way this is measured is that you can calculate under which king, pharaoh, emperor a certain eclipse should have occurred. And it's a very precise measurement because a total eclipse involves the moon and the sun, which have the same angular aperture exactly coinciding. And in fact, that eclipse will have occurred 3 hours earlier because of changes in rotation, which means it would have occurred at a different longitude. Time is not well known from antiquity, but the eclipse occurred in Babylon instead of London. That is known. And so you can actually go backwards and reconstruct changes in the rotation of the Earth. This was done by a man named Stevenson, who spent his whole life on doing this, using Babylonian, Greek, Chinese, and Arab ancient documents. And since that kind of a study involves not only a knowledge of astronomy, but also a knowledge of the literature of these four civilizations. It's a field that has never been overcrowded. But it indicates that, in fact, the Earth has slowed down due to tidal friction. I'm not going to say any more about that, but other than tidal friction, it has speeded up, and it has speeded up because of the deglaciation and the movement of the solid Earth towards, from the equator to the pole. And that number is an important number in what we will have to say. If there had been major movement of water from melting in the last 2,000 years from high latitudes towards the equator, this curve would have looked very different, easily measurable different, and it shows that melting was relatively minor in the last few thousand years. Now let me get to the main part of my talk, the last 100 years, because for the last 100 years we've had some observations, tide gauge observations, other observations. This is a plot from the year 1000 till the year 2000 of temperature, not sea level, temperature, mean Earth temperature in the northern hemisphere. And it's derived by a man named Mann and his collaborators using all kinds of observations. Some are direct temperature measurements, others are various fossil indicators. And the plot you get has been called a hockey stick. You see, it is fairly level, even goes down a little from the year 1000 to 1800. And then there is a sharp rise upwards at the end. This is a famous plot. It's been referred to a lot, and it's been viciously attacked by people who would like to say that this warming has not occurred. There's a Finn named Hamarante. Some of you might have seen the email correspondence that has occurred just in the last 6 months, in which he attacked, for various reasons, the validity of this plot. And I think the problem is still under dispute and under indication. I have another similar plot by another investigator, which is somewhat different. It's on a different time scale. It goes from the year 1400 to 2000. It also indicates a sort of a hockey stick-like behavior, but now the upward movement starts at about 1800, which was 1820 was the age of the time of the little ice age, but also shows a strong acceleration of warming towards the present time. Now this curve is a matter of some embarrassment, if you wish. Everyone talks now about the warming due to greenhouse gases associated with the Industrial Revolution, but that didn't really start until 1950, isn't it? That's when Industrial Revolution started. And that's when the greenhouse gases come in as being a source of warming. But you notice you get the same order of magnitude warming beginning much earlier, certainly beginning at the year 1900. So how can that be explained? Well, the standard understanding among people who study these things is that there are multiple causes, that the solar constant in quotes, varies, the radiation in watts per square meter that's coming in from the sun to the earth is known to be variable, and that early in the 19th century, in the 20th century, there was more than the usual amount of radiation, and that this is responsible for the early warming. Another factor is that large volcanic eruptions put a lot of dust into the atmosphere and cool the Earth, and that following that solar constant, there was less than the usual amount of volcanic eruption, which would also have the effect of giving you more than the usual warming. And that about at mid-century, the Industrial Revolution started, and that this took over. But we have this uncomfortable situation that there are three causes that appear to be of the same order of magnitude, and that the Industrial Revolution took over just as the solar radiation and the volcanic situation phased out to produce a curve of the sort that you see here. But that's the way it is being interpreted, and that's the way people talk about it. Let me talk about sea level now. This is a plot by Douglas of sea level beginning the year 1700. There were some tide gauges actually available that long ago in various European harbors, especially Amsterdam, and so it is possible to construct or attempt to construct a sea level curve beginning 1700 until the present. And the purpose of this plot is to show you that there is an indication of a more rapid sea level rise, in this case, starting about 1850. But very, very approximate, as you can see from those points. And that's not inconsistent with the two curves I've shown before. There was more warming at that beginning at about that time. And you see that prior to that, the sea level rose at a very small rate, 0.3 millimeters per year from this curve, as compared to 3 at the present. And then after that, according to that line, it became enhanced to about 1.5 on those units. So there is indeed a change in the sea level rise in the 19th century. Now, here is shown for the last 100 years, 1900 till 2000. Sea level at two very good stations in the mid-ocean, where as a whole things are more easily analyzed. The upper one is Honolulu, the lower one is Hilo, both in the Hawaiian Islands, both in mid-ocean. And I want to make 2 points. One is that there is no obvious indication of much of a change in the 20th century. If you look at Honolulu, you'd say it's going up at the rate shown, which happens to be 1.6 millimeters per year as drawn here, pretty well for the whole century. And so this problem as to why it should have risen at the same rate before the Industrial Revolution as after the Industrial Revolution comes in, and I think we must regard it as a curious circumstance that the change in the solar radiation and the change in volcanic activity and the human activity releasing CO2 came in such a way as to produce a fairly uniform curve. The other one is, why does Hilo have a different slope than Honolulu? You see that it's rising more rapidly. That is now understood, and that has to do with the fact that Hilo is sinking, the ground of Hilo is sinking because of volcanic activity. Honolulu is pretty stable, and the difference in slope you see there has to do with the stability of the ground where the tide gauges are placed, rather than anything to do with sea level. But it does point out the great difficulty of using tide gauges to deduce global sea level change, because the correction due to ground motion is a very big correction and a very uncertain correction. And only in recent days, John Orcutt mentioned GPS. Have the GPS work become accepted so that in future we'll be able to correct, using GPS measurements, the motion of the tide gauges themselves for the ground motion. Now, here is what's happened in the last half century, 20th century. I'm afraid we're in the 21st century. And the red curves you see are temperatures as observed, global mean temperatures as observed in the oceans. This is now an ocean slide. And you can see on the upper one a rise in temperature with big wiggles superimposed, but nonetheless a convincing change between 1950 and 2000 in the red curve. Those wiggles, and I'll come back to it, have to do with variability such as El Nino. You're all familiar. And it makes it very difficult to talk about global rise because the superimposed wiggles, as you see, are very large and have very little to do with the actual global rise, are sort of local basin phenomena, but they make it very difficult to extrapolate to get a good number. The upper figure shows the average heat content of all the oceans of the world from some work by Levitus, and translated into sea level, it gives you a rise in sea level of 1.8 millimeters per year. I'm using the same scale. The dotted curve, the dotted red curve, is the one that was predicted from some models. And as you see, the models do a fairly good job of predicting the rise, and also a fairly good job even of showing some of the wiggles. So there is some skill nowadays in models predicting total heat content of the oceans. And that model is consistent with what we know about greenhouse gases and the Industrial Revolution. And so on that basis you can make the sentence that the rise since 1950, 1960 in the ocean heat content is consistent with greenhouse gases and the Industrial Revolution. The lower curves show the warming at various ocean depths, particularly interesting to oceanographers. 500 meters, 1,000 meters, 1,500 meters, 2,000 meters. And the scale has been increased, doubled as you go deeper. So it's a little difficult to interpret, but the proper interpretation is that the heating pretty much stops when you get down to 1,000 meters. Almost all the heating takes place in the upper 1,000 meters of the ocean. That's where the additional heat content from the Industrial Revolution has come. That's the solid curve, the observed. The dotted curve are again the model predictions, and they're pretty awful. When you go deep, you see you get much more warming on the model prediction than is actually the place. You see the dotted curve indicate that you get considerable warming below 1,000 meters when in fact you don't. And that just, I'm mentioning that to take away some of your confidence in these numerical schemes of predicting. They're not working very well. But anyhow, this very large effort by Levitus of looking at 5 million ocean temperature measurements does indicate that you should have a rise of about 1.8 millimeters per year in that time, and that most of it is due to warming in the upper 1,000 meters. Now, this is the only kind of difficult transparency that I would like to use to indicate to you what the recent history is. You also get an effect from changes in salinity, which also affect the change in density. And the thing I talked about when I talk about thermal expansion is essentially that the density of the ocean decreases when it gets warmer, decreases when you have less salt, and that decreased density is associated with a higher sea level, and that's indicated in the formula on the upper left. Now, in 1995, the first global estimate was made when people became very much concerned with global warming. IPCC stands for International Program for Climate Prediction. Those are the people who are constantly being quoted in the press when it comes to temperatures. And the prediction in 1995, not so long ago, was that sea level was rising, let me use the number 1.8 millimeters per year, and that most of it, in the left column here, most of it was due to thermal expansion, and a very small part, 0.2 out of 1.8, was due to continental melting. And the figures of continental melting are very interesting. Remember, the total was 0.2 with enormous error bars, plus minus 1, means a very, very poor average. Glaciers in Europe add about 0.3, and that's probably the only good number that people have been able to do. Glaciers in Europe have been disappearing. Greenland has some, but surprisingly little melting, adds 0.1. Antarctica, which has nearly all of the ice in the world, is stable and not melting. And finally, the last figure is the most interesting one. It says minus 0.3. If you build new dams and new reservoirs and store water, it's just the opposite effect of melting waters. You take water out of the oceans and put it on land. The Chinese have apparently built 20,000 reservoirs. And the estimates of that international commission is that they more or less have stored as much water as the alpine glaciers have melted. It's anti-intuitive. It's the figure that the national body has published, and I have to accept it. But at this point, you see, there isn't much melting going on, according to the IPCC report. And that has not much changed. It's one of the riddles. There is at this time, although a lot of arguments going on, not a clear idea where the melting comes from. Now, 5 years later, in 2000, Levitus, I just showed you his results, did his first survey of ocean temperatures, and his finding was, and you've just looked at that the warming of the ocean can only contribute 0.5 out of 1.8 millimeters per year. And so the IPCC solution that most of it was thermal expansion, very little was melting, had to be reversed. If you believe the figures, it's now 0.5 from thermal expansion and 1.3 for melting to make a total of 1.8. And so instead of having a warming ocean, you have an ocean growing because of melting. But nobody has come up with a good source of that additional water. And that is true today. The people who've done the glaciology have not come up with the necessary large amount of melting, although there have been some recent papers saying that we have greatly underestimated the Alaskan glaciers. And I'm not an expert on that field. I would just suggest to you that there's some unknowns in that are very real. And then further down the line, a few years later, a partner of Levitus named Antonov, for the first time attempted to measure whether the ocean is changing its salinity, whether there is freshening. And he found that on those units, the salinity effect was small, about 10% of the temperature effect, and not of first order. Now, my own contribution to this field is very small, but comes in on that point. Since the glaciologists couldn't agree among themselves how much melting there is, I thought that one could tackle the problem from the other side The freshening of the ocean should indicate how much water has come in. Fresh water has come in from the continents. Why not try and attempt melting, to estimate total melting using those melting figures, the freshening. The freshening figure, by the way, is very poor. It has big error bars, as you can remember. It's a very hard thing to do. But nonetheless, we attempted that, and we ran into a similar difficulty. It makes a lot of difference as to why the freshening of the ocean took place. For example, if it's due to floating ice, like in the Arctic, it doesn't change the sea level at all. You know that if you have a martini filled to the very rim with an ice cube melting, with an ice cube floating on top, the melting of the ice cube will not spill over your martini. It's a very important practical consideration. Because the mass of the ice cube is just balanced. It's the old Archimedes principle. So if you try and use the observed freshening of the ocean to ask how much of it has come, how much of it has introduced changing in sea level, you have to subtract the amount of freshening that you get from the floating ice. And that turns out to be very, very poorly known. There are really two surveys that have been done. One starting about 30 years ago with the first nuclear submarines going under the ice to the pole and using inverted sonars looking upwards and measuring the lower boundary of the floating ice. And that is the main method. And that has indicated that in the last 30 years, the ice in the Arctic has thinned from an average of 4 meters to an average of 2 meters. Enormous difference. And you've seen articles suggesting that in your lifetime, the Northwest Passage will be open. It's based on these measurements with upward-looking sonar. Another method used by the Russians is based on the penetration of ocean swell into the ice field. You can use those measurements to make an estimate of ice thickness. Complicated, very uncertain, but it gives about 1/6 the result, much, much less. And at the moment, the amount of melting ice, sea ice, is really not known. And that's a problem that ought to be solved because it's not impossible. But if you accept the upward-looking sonar figures, you find that you get agreement with what I mentioned, the 1.3 millimeters per year coming from continental sources for melting of continental ice sheets, and 0.5 from thermal expansion. So at least that is consistent. That does not tell you where the melting takes place, but it's consistent with melting of some of the ice sheets in the world. Oh, this is a French plot just to show that if you plot sea level against temperature and include the changes in salinity on the right, as opposed to only using temperatures on the left, you get a somewhat less scattered plot, indicating to you that you should use the salinities as well. It's a bit of a second order consideration. Now I'm going to the last 10 years. Last 10 years being very different than the last 100 years. The upper plot showed where the tide gauges are located, on the basis of which most of the results I've discussed are coming. The lower plot shows satellite measurements of sea level from Topex Poseidon, and it is a dramatic indication how vastly better the new measurements which have just become available in the last 10 years are. The oceans are almost covered by the successive orbits of the satellite, so that you get an order of magnitude better coverage from the satellite measurements. The sampling is hugely better than it was. Now, Topex Poseidon is a satellite that measures out the sea level by sending a radio wave downward, having it reflected, going back to the satellite, and measuring the time it takes. It is incredible, isn't it, that this method has now worked to a precision where we can say something about changes in sea level of a few millimeters per year. But it has. And so what I wanted to show you here is the enormous improvement in the coverage due to the Topex Poseidon altimetry. The second great improvement is that not only covers the ocean more densely, but it also covers the whole global ocean. You notice big gaps in the southern hemisphere in tide gauge data. Those gaps disappear. And the third and the most important point is that Topex Poseidon, the satellite altimetry, measures sea level relative to the center of the Earth and not relative to the ground, which itself is moving and therefore makes tide gauge estimates very, very difficult. So this is a first order improvement of what people have been able to do and leads you with a great deal of optimism for the future that we'll be able to get good numbers. Here is a picture based on those satellite measurements for the period 1993 to 2004, the last 10 years. And it indicates an increase in sea level of 2.8 millimeters per year. Notice I previously said that the typical value for the early century was 1.8. So there has been an acceleration. I think that is almost without doubt. And the sea level is now rising more quickly, considerably more quickly than it did in the past time. And again, the difficulty in getting very precise number has to do with these wiggles. We call them decadal variations, El Nino related. You see a big wiggle, for example, in 1997, and that is to some extent understood now. It has to do with the disturbances related to what we include under this name. Now, I'm referring to that one big wiggle, and I want to just say a little bit more about this, because I said it is now understood. This is a lady up at JPL in Pasadena who has done this work, Jean Dickey, and the curve that's marked PGU on both upper and lower slides is the inferred effect of post-glacial uplift. And what we're here plotting against time for the period 1982 to the present is the size of the equatorial protuberance of the Earth. The equator having a bigger radius than the pole. The Earth is not a sphere. I mentioned that before. And it is measured in the most curious way. A satellite orbit, if the Earth was a perfect sphere, would remain in the same plane, but because of the equatorial protuberance, it gradually precesses around the world. And that's why you get these different orbits at different times. And they have satellites that are so precise in their location that you can not only measure the rate at which it precesses, but the rate of change of that rate. So I'm showing here essentially the size of the equatorial protuberance on the upper curve, and the black line you see is the one obtained from my second slide based on ancient eclipses. Those also indicate this kind of thing. And isn't it amazing that these two very different type of observations, one finding out where ancient solar and lunar eclipses took place, the other one measuring the precession of a modern satellite, should give you essentially the same rate at which the equator is getting smaller, if you wish. And land is still moving to the poles in response to the glacial, to the removal of the ice sheets. But notice something very odd happens in 1996, and it has to do with this El Nino event. There is a reversal of that effect. The equator is suddenly getting bigger for a few years, and that effect has been associated with an El Nino type redistribution of mass. The work has been done quantitatively, and you find that the redistribution of ocean mass during El Nino can be so large as to affect really the orbits of a satellite. And so we do know something about these perturbations and what they're due to. Now, the next 10 years, this is my transparency. I'm being very, very carefully. And I don't want to put anything down because there are too many loose ends. I just want to show you that slide. I want to make a few concluding remarks. First of all, there is no doubt that the satellite measurements of sea level, the Topex Poseidon altimetry, is going to revolutionize the subject. We now have over 10 years of data. It looks absolutely wonderful. And you need to have a few decades in order to average out these large El Nino-like oscillations, and you'll get some very good numbers. There is a new satellite up, and I don't know the results. There may be some people in this room who do. It's called GRACE. And it is I don't think say much about the configuration, but it measures only that part of sea level which is due to additional mass, namely melting. And that's been up for a year and a half, I think, now. And we ought to be getting some independent numbers on the amount due to melting. And that will make all the difference in the world in trying to interpret this. Regarding the floating ice, which interests me, trying to make better estimates of the extent and rate at which the floating sea ice is disappearing, there are some new ideas, and the Norwegians are putting some more measuring equipment into the Arctic, and over the next few years there will be significant progress made. So I've shown a sort of a complicated history. In the last 20,000 years, the big glaciers, the big ice sheets have melted. They gave you speeds of up to 10 millimeters per year of sea level rise. That stopped about 4,000 years ago, was entirely due to, of course, to melting. Thermal effects were negligible. Then in the last 100 years, the thermal effects, the ocean warming is significant, but I think still less than the melting effect. I think something like 1/3 to 2/3. The last decade has seen a definite acceleration in the rate of sea level rise. It's now apparently about 3 millimeters a year, and about half thermal, half melting. And there is a student in the audience who is doing some work on this problem, Josh Willis. Maybe he will say a word after I sit down. But there's a great weakness I want to mention to the whole discussion I've given you. I made you think of these changes as being smooth. They may change, but they change smoothly from one decade, from one century to the other. Jeff Severinghaus, he is not here, I think, at Scripps, has done some work in the last 5 years which indicate that there have been cases in the last 20, 30,000 years when changes occurred that were extremely rapid. He's just come back from the Antarctic, where he's collected some ice cores that indicate ice cores give you the possibility of studying ancient atmospheric bubbles. And from those he deduced that changes of the order of many degrees, maybe 5 to 10 degrees, can occur in a period as short as 10 years. And that doesn't fit in with that smooth picture I've given you, and I don't really know how to reconcile those. We don't understand that, but you must hold in mind that such rapid changes are not out of the possibility from what we know about this history. So that's the end of my story. As you know, it's a very political issue, I'm sorry to say. You find that this story I gave you is full of holes, full of uncertainties, and they are the professional climate skeptics who take the view that so little is known that you should do nothing. I'm what's the opposite of a skeptic? I'm a climate activist, and I think enough is known that something should be done, the opposite view, and I will give you an example of what we've done. If all the remaining ice caps in the Arctic and Greenland would melt, sea level would go up another additional 360 feet. We have built our house right near here at an elevation of 360 feet. That's my activism thing. So when Scripps goes underwater, and when this aquarium will be underwater, we'll still be sitting at home dabbling our toes into the warm waters of the Pacific. Thank you. I think about a quarter of the world's ocean is above 1,000 meters. So what happens in the lower is very important. We know virtually nothing about the abyssal ocean because there haven't been enough measurements, and we might have a surprise coming on the warming of the lowest few thousand meters. It's a good question.